Nobody entangled a whole crystal until now. A centimeter-sized piece of matter small enough to sit between two fingers was found to carry quantum entanglement across its entire structure, not between two isolated particles in a controlled lab, across the whole crystal collectively at a scale physicists had never measured before. And the team behind it, Prof. Silke Bühler-Paschen and her colleagues at TU Wien, in Vienna, published the result in Nature Physics, one of the most rigorous scientific journals on the planet. Here is what quantum entanglement actually means, because the standard explanation has been repeated so many times, it has stopped meaning anything. Two particles become entangled when their quantum states are linked so completely that you cannot describe one without describing the other. Measure one, and you instantly know something definitive about the other, no matter how far apart they are. Scientists at Caltech describe it as an emergent property, something that arises from the connection between particles, not from any single particle alone. For decades, this was a phenomenon that lived at the smallest possible scales. Individual atoms, photons, carefully controlled pairs. The idea that it could exist at a scale you could see with your own eyes felt like a different category of physics entirely. The crystal the TU Wien team studied is classified as a strange metal. That name is not informal. Strange metals are a formally recognized class of materials whose electrical resistance defies the rules that govern ordinary metals and whose electron behavior cannot be modeled by the standard frameworks physicists rely on. They sit in a zone where existing theory breaks down. That is what makes them unusual candidates for this kind of investigation, and that is exactly why nobody had looked there before. The assumption was that entanglement could not survive inside bulk matter at this scale. Maintaining it required near-perfect isolation, extreme conditions, carefully engineered systems. A crystal you could pick up with your fingers was not on the list. The TU Wien findings suggest that assumption needs to be revisited. Entanglement was not just present in the crystal, it was measurably high, and it was a collective property of the whole structure, not a local effect tucked into a corner of the atomic lattice. Part of why this went undetected for so long comes down to instrumentation. Detecting entanglement across a macroscopic object requires experimental sensitivity that has only recently become available. Part of it is that nobody was looking inside strange metals for this. The question has now shifted from whether entanglement can be engineered into a system to where else it might already be hiding naturally. That shift matters for a practical reason. Quantum computers today are fragile. They require extreme isolation and temperatures close to absolute zero to keep entanglement stable long enough to be useful. If naturally occurring bulk materials can sustain macroscopic entanglement on their own terms, the path towards stable, scalable quantum technology looks different than it did before this result. The bottleneck that has defined quantum engineering for years just changed shape. Subscribe if a story like this is what you came here for. The crystal Professor Bühler-Paschen and her team held in their hands is roughly the width of a thumbnail. What it points toward is not small at all.